In this video, we're going to talk about torque and how we can rotate objects. So we define torque as an interaction that is capable of causing an object to rotate, right? So you pushing on a door to open it, or me twirling my pen, right? I caused my pen to rotate. I applied a torque to my pen. The fact that we say the word interaction, that is, I need two objects to create a torque. I need some force between those objects. So torque is deeply related to force, but it is not the same thing as force. Okay, so let's begin just by thinking about what types of forces would cause objects to rotate. So first, if I want an object to rotate, I need some axis of rotation, right? So imagine that I have a door. So this is you're looking down from above on a door. The door rotates because it is attached to hinges, right? So there is an axis around which the door can freely rotate. And because of that, if I apply a force to the door, it will cause the door to rotate, right? So right now, I want you to go pause the video and do a quick test. And the test is find a door and try to push the door open by pushing here with some force. This is point 1. Apply a force here. Apply a force here. And apply a force here. So just go push on a door to try to open it at these 3 spots along the door, close to the hinge, in the middle of the door, and on the end of the door. And while you're doing it, think about, why are the handles always over here, right? Why is the door handle always on the end? Hopefully you have gone and actually pushed on a door now. And with these 3 locations on the door, you should have found that this was hard to open, right? This was easier, and this was easy to open the door, right? The further out you push on the door, the easier it is to rotate the door, which means that we get more torque, because torque is an interaction that is capable of rotating our object, and it's easier to rotate our object when we push out here at point 3. Okay, so what we can do now is we can try to write a sample. So I'll call this a test function for torque. So let's say torque should be proportional to how much force you apply. So if I push really hard, I should be able to get the object to rotate more. And it should be proportional to r, the distance, so that I'd call this r3, the distance away from the axis of rotation where I apply that torque. Okay, so that makes sense. Further away makes it easier to rotate, and more force makes it easier to rotate. If you've ever seen a wrench set, right? So if you have like a bolt, which I will draw as a square, and then you want to rotate that, you get a socket wrench, socket, handle, and you pull here, right? You apply a force here, say downward. That's because if you tried to grab the bolt directly, right, you would have a very, very small R, right? If I tried to grab it, say I grabbed the handle here, I would have a very small R. It would be difficult to get my bolt to rotate, right? But if I grab out here, I have a much larger R, easier to rotate. Exactly the same principle as the door. Okay, so we have this kind of sample function for torque, but that's not quite the whole story, because it matters how we apply our force. So we now know that the torque should somehow relate to the amount of force that we apply and how far away from our axis of rotation we apply that force. But the last thing that we need to think about is what direction are we applying that force? So if you push this way on a door or you pull on a door handle, you can get the door to rotate. But if you try to pull directly outward on the door, you will not have such great luck. So this force appears to give no torque. Because no matter how hard I pull this way, right, the door is not going to start to rotate. Whereas this force here definitely applies a torque. So now, if we know that F1 here is a good torque and F2 is a bad torque, we could think about what if I applied a force at any arbitrary angle? So let's imagine that I apply a torque from this point here at some angle theta, right? So I have some force here, it's applied upward at some angle theta, right? If you remember from our uniform circular motion discussion, we can think about a rotating system in terms of tangential and radial components, where radial points outward from where we're rotating around, from our axis of rotation. So we call outward from the axis of rotation positive and inward from the axis of rotation negative, right? So this is the radial component of our force F, right? This radial component is pulling the door outward and provides no torque for us. Because forces that are directly away from or into the axis of rotation don't provide a torque. The other option is that we have tangential forces. Tangential forces are forces that are perpendicular to the radial forces. And in general, we call tangential forces that are counterclockwise. So if it's a tangential counterclockwise force, we call that positive. And if it is tangential and clockwise, we call that negative. So if I just have some arbitrary thing here, any force that attempts to move me, so the force wouldn't point in a curve, but if it attempts to move my object counterclockwise, then I call that positive. And if it attempts to move my object clockwise, then I call that a negative torque, right? So this torque here is attempting to pull the door. So this is my door here. It attempts to pull my door outward, which gives me no torque. And then it also attempts to push my door upward, which gives it a counterclockwise rotation, right? The door is going to rotate this way. So this is a tangential force. And I know that this force in particular is positive because of my tangential coordinate system, where counterclockwise torques that generate a counterclockwise motion will be positive. All right, so in looking at this picture, we can see that the tangential component of my force looks like the magnitude of my force multiplied by the sine of my angle theta here. So this is theta, this side here is my hypotenuse, the magnitude of my force, multiplied by the sine of theta. This is the component of my force that actually gives me the torque. My radial component does not help. So I can finally write down that my torque should be given by how far away I am, my radius, multiplied by the magnitude of my force, multiplied by the sine of theta. And in this case, the way that this is set up, your torque will always be positive if you use this formula. And because your torque will always be positive here, you have to manually assign the sine of the torque when you use this particular method. So here, I would manually assign my torque due to this force to be positive because this force is trying to rotate my system in the counterclockwise direction. Before we move on to another example, let's just quickly talk about what this theta actually means. So if I look here, there's a line that comes from my axis of rotation straight through the point where the force is being applied. And this line here is my radial vector. So R, this vector, points from the axis of rotation to the point where the force is applied. So my R vector here points from the axis of rotation to where the force is applied. And theta here is always the angle between my R vector, which really the direction of my R vector, right? Because if you continue my R vector out, it comes parallel to this F radial here. So it is the angle between my R vector and my force. So theta is the angle between my R vector and my force vector. And figuring out this angle is going to be key to finding the torque in any arbitrary situation. Now let's look at an example where we're not completely horizontal, and we will figure out how this theta works. Now let's imagine that we have a door again, where the door is now at some angle and we are applying a force this way, right? We can clearly break our force up into our components again, and we can try to figure out what this value is here. Okay, so I want to be a little more careful here about finding the angle between my force vector and my radial vector. The way that we want to do this in general is that we want to draw the radial vector, R, and the force vector, F, with their base, with the tail of the vector at the same point, and find this angle here, theta. So in order to do this, I need to give you, say, this angle is 25 degrees. That's fine. So if this angle here between the horizontal and R is 25 degrees, and F is horizontal, then theta just equals 25 degrees. Okay. So now this angle here, which is the continuation of r, must also be 25 degrees. And notice that only this part here, which is perpendicular to the r vector, actually matters, right? This is our f sine 25 degrees force. That is what's causing the torque. Okay, so in this case, we can find the torque on the object as magnitude of r, magnitude of f, multiplied by the sine of 25 degrees. And notice that this force here, if I draw my arrows on my vector, the tangential component, the component that's causing our torque, points in the counterclockwise direction. It's attempting to get the door to rotate, in the clockwise direction. It's attempting to get the door to rotate in the clockwise direction, so we are going to pick up a minus sign out front here. So our torque in this case is negative 2 meters multiplied by 30 newtons multiplied by the sine of 25 degrees. And that's our torque. That's it. You can plug this into your calculator. It will give you a value and tell you how much torque you are applying to this door. Okay, let's try one more example where it's a little trickier to find the angle between the radial vector and the force vector. Now let's look at an example where I have some unknown angle between the radial vector and the force vector. So in this case, I've given you the magnitude of the radial distance from the axis of rotation to where the force is applied. I've given you the magnitude of the force that is applied, and I've given you two angles. So the first question you should ask is, which of these angles is theta? Or is neither of these angles theta? And it turns out that neither of these angles is theta. I have given you the angle of these two vectors relative to different axes, but not the angle of these two vectors relative to each other. So we're going to use the exact same technique that we've used before in finding the angle between vectors. Namely, we are going to draw both of the vectors emanating from the same starting point. And then I'm going to insert any information that I know. So this is my force vector making an angle of 30 degrees with the negative y-axis. And this is my radial vector making an angle of 160 degrees with the positive x-axis. Now the angle that we are really looking for is this angle. The angle between the radial vector and the force vector. That is our theta. Now, there's a couple different ways that we could find this. The simplest one that I see at the moment is if I realize that this angle is 30 degrees, then this angle here must be 60 degrees because it makes 90 degrees between the x and y axes. So then this angle here must be 160 degrees plus 60 degrees, looks like 220 degrees. And that angle is bigger than 180 degrees, and we always want our theta to be the smallest angle between the two. So theta should be the smallest angle between r vector and f vector, which means that theta should be less than or equal to 180 degrees. So if my r vector goes over 180 degrees, then the angle on the other side becomes less than 180, and that's what we're interested in. But here we've found this larger angle, and so we know that theta is just 360 degrees minus 220 degrees, because obviously a full circle is 360 degrees. So I've gone 220 degrees and then I need to go another theta. So theta must be the difference between them, which looks like 140 degrees. So we have now found theta, the angle between the radial vector and the force vector. So our torque equals magnitude of my r vector multiplied by the magnitude of the force vector multiplied by the sine of 140 degrees. And you can just plug this all into your calculator and you will end up with a value for torque. Now, again, this will always come out positive. So I need to assign manually the direction that this torque is taking, whether it is clockwise or counterclockwise. So the way to do that is look at this picture, and if I draw my, sorry, that is not what I want to draw. I want to draw my force vector in terms of radial and tangential components. So I'm going to take my force vector here, and I'm going to draw the component of it that points along the axis and the component of it that points not along the axis, right? So I've broken it down. This one points inward, so the radial component is pointing in towards the center, right? So this black line here becomes the radial component, and this becomes the tangential component. And the tangential component is what causes our torque. And you can see that this tangential component here is attempting to move my whatever object I'm moving in the clockwise direction. So this is again a positive torque, right? So in order to find your positive or negative, you have to break your force up into one of your lines should point right along the radial direction, whether it is toward the axis of rotation or away, depends on the direction of your vector. And then the line perpendicular to that, which is your tangential. And you have to just figure out if your tangential force here tries to push the object in the counterclockwise direction, which is positive, or in the clockwise direction, which is negative.